Okay, so maximal domain means I try to determine what x values will make the function exist. So for a square root function, I need 2 minus x to be greater than or equal to 0. Geez, what's going on there? Greater than or equal to 0, which means 2 is greater than or equal to x. So as long as x is less than or equal to 2, we're okay. All right. Similar hyperbola, we just need the domain to not be 0. So in this case, I need x minus 3 to not equal 0. So x cannot equal 3. So we could say x is an element of R excluding 3 if we wanted to formally write it. All right, find the inverse function of this particular thing here first. So the easiest way to find an inverse, we swap the x and y. I think the best way to do these is to do the division first. So I need 2x plus 1. It has to be divided by, let's just scrub that. I'm going to need 5x plus 3 to go into 2x plus 1. So I need 5 to go into the 2. So I've got to multiply this by, what do I multiply the 5 by to get 2? And if I multiply by 2/5, yeah? So 5 times 2 is 10, divided by 5 is 2. So 2/5 times 5 will give me 2x. 2/5 times 3 is 6 on 5. If I subtract them, 2x minus x is 0, which is good. 1, which is 5 on 5, minus 6 on 5 is minus 1 on 5. So I end up with 2/5 remainder, negative 1/5. So that means I can write f of x to be equal to 2 on 5 minus 1 over 5, and whatever was on the denominator, 5x plus 3. Okay, that looks messy, but it's a messy question. All right, so first things first. So now let's find the inverse. We have to find the inverse, so that's right. So for the inverse, we swap x and y. So that means I'll end up with x is equal to 2 on 5 minus 1 over 5y plus 3. So actually, in some ways, maybe if we multiply everything by 5 at that point, I've got a 5 on the bottom there, 5 on the bottom there, so I could go 5x equals 2 minus 1 over 5y plus 3. Maybe I might take the 1 over 5y plus 3 onto the left-hand side, and that becomes 2 minus 5x. Flip it upside down, I get 5y plus 3 equals 1 over 2 minus 5x. 5y equals 1 over 2 minus 5x minus 3. Finally, we'll divide by 5, and that's my inverse function. So I'm going to say inverse of x is equal to 1 over 5 at the front, 2 minus 5x minus 3/5. So there's my inverse. The domain and range of the inverse, or the domain of f inverse, is where 2 minus 5x is equal to 0. So need 2 minus 5x to not equal 0 for the domain. So x cannot equal 2/5. So we can say the domain of f is R except for 2/5. the range of f inverse, well, that's equal to the domain of f. And if I look at the domain of f, go back up to the original function in green here, I need 5x plus 3 to not equal 0, so x cannot equal negative 3/5. So the range of f will be r excluding negative 3/5. Okay, so it's a messy algebraically. We could sort of check things out a little bit here. I'm saying the domain is r except for 2/5. If I compare that to when I swap the x and y, the original function, the vertical translation was 2/5 up, so that's where my horizontal asymptote will be. So that range becomes a domain of the inverse, so it ties across reasonably well, but messy, and I didn't leave you much room. Sketch the graph of and find the inverse function. Okay, so it's a square root function. -3 inside the function means I've gone to the right 3 units. So if I put 3, now just try and pick a point. So if I put x equal to 4, I'll get 4 minus 3, which is 1. Square root of 1 is 1. So it goes through the point 4, 1, which is there. Maybe I could argue that that point there is 7. 7 minus 3 is 4. The square root of 4 is 2. So it goes through the point 7, 2. So the function looks a bit like that. That's the point 0, 3. And find the inverse function. Okay, so the inverse function, we'll do that in blue, means I can put x equal to square root of y minus 3. So x squared is equal to y minus 3. Y is equal to x squared plus 3. But obviously, the domain of f, even if I look at the range of f, what if I do it that way? It makes more sense because I've got the graph there. So the range of f is from 0 to infinity, which means that's what the domain of my inverse function will be. So it's from 0 to infinity. So if I put x equal to 0, y is equal to 3, and you can see there's going to be reflection. So, oops, I forgot to write down f inverse of x is equal to x squared plus 3. And if I put x equal to 1, I'm going to get 4. So the point 1, 4 might be up there. If I put x equal to 2, I get 7, which might be up there. So the inverse will be up here like this somewhere. That's the point 0, 3. And I should go back and change my y-intercept, of course, to be 3, 0. That was poor. And it kind of makes sense. We know graphically the inverse function is a reflection about the line y equals x. So that looks like it fits. It looks reasonable, doesn't it? All right, f of 4. So we have a hybrid function here. So the top part of the function is only valid if x is greater than -2. The bottom part of the function is x is less than -2. So f of 4 will equal, 4 is in the top, -2 times 4 plus 6, -8 plus 6, which equals -2. Sketch f of x stating the range. So, looks a bit thick, that line for my liking. -2 is the key part, isn't it? So I'm just going to put, it's not an asymptote, but this is the key part of the graph. Right, that's where things change over. So if I want to sketch, well, I know what f of 4 is. 4, I should get the answer of -2. So where's there's 4, there's -2 down there. So I'll do the top one in red. So it's a negative gradient with a y-intercept of 6. So there's the y-intercept there. If I get my ruler out, there it is. So it's going to look something like that. Does that make sense? So -2x plus 6 equal to 0, -2x equal to -6, x is equal to 3. So there's my x-intercept, that's good. Solid dot, so if I extend my dotted line up there, I have a solid dot there, and at x equal to -2, I get y equal to 10. Okay, if I grab my blue, now function, now I'm doing x plus 2. If x is equal to -2 in that function, f of -2 will equal -2 plus 2, which is equal to 0. So that's solid, sorry, it's a hollow dot. So in blue, I've got a hollow dot there, and it's got a positive gradient with a with the y-intercept of +2. So this graph, so the gradient of that line is 1. So it's going to look a little bit like that. Okay, state the range of f of x. So the range is, well, what values? The maximum y value is up here, was at 10. I go all the way down to -infinity from this one here, or from both of them. So from 10, oops, we want to have round bracket, don't we? Minus infinity to 10. All right. Solve h of x is equal to x squared plus 4x. Find where g of x equals the inverse function of h of x. So we know, find g of x where g of x is the inverse function. All right, so again, we go to swap our x and y values. If I just do that, like we'd write y equals x squared plus 4x minus 1, swap x and y, I get x equals y squared plus 4y minus 1. And so we have y's, multiple y's everywhere. Now, it doesn't necessarily matter which order you do it, but once we see, we want to write our quadratic so that there's only one representation of that y value, which means we need to complete the square. And I would much rather complete the square on the original function, okay? So if I write the original function, y equals x squared plus 4x minus 1. Let's complete the square, x squared plus 4x, halve the middle term and square it. So hopefully we're getting much better at just being able to go x plus 2 all squared minus 5. So that's what that function is. So now if I want to find the inverse, I swap x and y. I get x plus 5 equals y plus 2 squared. Take the square root. So I'm going to put y plus 2 equals plus or minus the square root of x plus 5. So y equals -2 plus or minus the square root of x plus 5. Now there should be some information here about the domain because we shouldn't have the plus or minus there for our function because it won't be a function. So up here we say x has to be greater than -2, which means the range of my, if x is greater than -2, that means the range of my inverse function has to be greater than -2, which means in here, I'm going to put the plus, because if I subtract, I'm going to get -2 minus numbers, -2 minus 4, -2 minus 6, -2 minus 8, and I'll get bigger and bigger negative numbers. And yet from the original definition of the function, I should be getting bigger numbers, more positive numbers. Find f of g of x. Oops. Okay, so that's okay. So I guess formally we probably should write g of x is equal to -2 plus the square root of x plus 5. Okay, next question. All right, sketch the graphs of h of x. Oh, we've got more to go. Stating the domain and range. Let's go back here. So let's go. Y equals x plus 2 all squared minus 5, and the plus the square root of x plus 5. So let's go blue for the original function. And we have a turning point at the point -2 minus 5. If we get an x-intercept, I'll get x plus 2 squared minus 5 equal to 0. 2 squared equals 5. So x will equal -2 plus or minus the square root of 5. So the square root of 5 is slightly bigger than 2, isn't it? So -2 plus 2, well, -2 plus the number slightly bigger than 2 will be slightly positive. So we've got a turning point there at -2. We've got an x-intercept there at the point -2 plus root 5, 0. If I put, is there a nice value there? Actually, if I put x equal to 1, I'll get 3 squared, which is 9 minus 4, minus 5, which is 4. So it goes through the point 1, 4. So maybe it goes a little bit like, if I put 2 plus 2 is 4 squared minus 5 is 11. So maybe it goes a little bit like that. We have to state the domain and range. So the domain is from -2 to infinity. The range is from, what is the range from? -5 to infinity. Okay, so let's go into red now for my inverse function. That's shifting it 5 units to the left. That's shifting it down 2 units. Also, I know that that point there, the stationary point, which is at the point -2, -5, will be at the point -5, -2. Yeah. For the inverse, so -5, -2 is -5, -2 might be about there somewhere. What was the y-intercept of the original? The y-intercept, I got 2 squared is at -1. So that point there is at the point 0, -1. So if that's my y-intercept, my x-intercept will be at the point -1, 0. Red pen. It's going to be an ugly graph, boys. That x-intercept was at the point 0, barely bigger than 1. So the y-intercept will be at the point barely bigger than 1, 0. All right, well, what's some other points we can map in? Scale doesn't really work all that well. If I put the point x equal to 4 for the inverse function, I'll get 4 plus 5, which is 9. Square root of 9 is 3. -2 plus 3 is 1. So it's got to go through there. So you can see how really tight the inverse is. So it's going to look something like that. So that point there is the point -5 -2. Right after about a point of intersection, we can keep that point continuing. I guess we do know though that the domain will be from -5 to infinity, and the range will be from -2 to infinity. We might get that on Desmos and have a look. All right, another similar sort of question. Sketch the graph 5x² minus 5x between 5 on 2. So again, if I complete the square on that, I can write f of x is equal to x minus half the middle term, square it, which is 25 on 4, and then I've got 0 left over. So that's what it's going to look like. So we've got a turning point at the point 5 on 2, -25 on 4. So where's that? 2.5, -25 on 4 is about -6, -6 and a bit. So we'll call it, what's 5 on 2 is 2.5, that's 3, so that's that one there. So we'll call it about there. If I put x equal to 0, y is equal to 0. So that would go through there if I wanted it to, but it's not. If I solve my other x-intercept, x will be 0 and 5. So it goes through 5. So it's going to look something like that. Sketch the graph of the inverse. It doesn't say, and state the domain or range of the inverse. All right, so there's that one. So to find the inverse, swap x and y. So I know that I can put x equal to y minus 5 on 2 all squared minus 25 on 4, x plus 25 on 4 equals, take a square root, running out of room, so I'm going to say y equals, the 5 on 2 goes across, plus or minus the square root of, and again, given that our domain is positive, that means the range of our inverse has to be positive values. So I can say f inverse equals 5 on 2 plus. All right, so let's just sort out a few things here with our blue function. We'll just tidy it up a smidgen just to make the inverse a bit easier. Let's get our turning point in there, which is at the point 5 on 2, -25 on 4, and our x-intercept at the point 5, 0. Because now that we go along to sketching our inverse function, we know that everything is swapped. So -25 on 4 is about -6. So obviously our axis is a little bit out of whack here. So I reckon on your worksheet, I've changed the scale of the axis. So let's get the points in that we can. 5, 5. So we know it's going to go through there. Okay. -5 on 2 is the new y coordinate of the turning point. So what's that, 2.5? So it's along this line. So it's going to be out here somewhere. Okay. And we know they join along the line y. So the scale's going to be a little bit out for a range of reasons. But along the line y equals x, so maybe, maybe it goes a little bit like that. So on this scale, it looks skew-if, but I'm hoping on your newer scale that I updated, it should come out a little bit tidier. Okay. Have we got a domain and range stated yet? The domain and range of the F inverse. Okay, so the domain of F inverse is the range of the original. So that's going to be the range of the original, which is from, go square, -25 on 4 to infinity. The range of F inverse will be the domain of the original, which is 5 on 2 to infinity. Yeah, look, it's a little bit cluttered, that one, lads, but yeah. Oh, so if I get time, I'll redo it for us. Let's go to question 8. I'll go to a green. X squared minus 2, explain why the composite function does not exist. So straight away, we're going to draw a domain range table. So I'll call that domain range, we'll call that F, G. So let's go to F. F is the quadratic, so we've got the domain there, 0 to infinity. The range of that, what's a parabola, shifted down 2 units, isn't it? So the range is going to be from -2 to infinity. It's a little bit tight for room there, I might make it bigger. So bear with me, just so we can see it. So 0 to infinity, I hope it was, -2 to infinity. And for g of x, we've got the domain there on the screen, so we'll go, oops, why has it got a square bracket? Round bracket, minus infinity, up to the point 2. So that's that. And what's the range of that function look like? So we better, well, if I put 2 into that function, I get 0. So I'm thinking that's going to be the smallest. And if I put really big negative numbers in there, I'm going to get 2 minus a really big number, which is positive. So I'm going to get positive infinity, aren't I? So for the composite function to exist, I need range of the inside to be a subset of the domain of the outside. So that implies the range of f, which is 2 to infinity, to be a subset of the domain of g, which is minus infinity to 2, which is false. So that's why it doesn't exist. And we need those values there. Restrict the domain of f so that g of f of x does exist. So why doesn't it exist? Well, these positive infinity numbers are too big for that positive 2. So the green function, f, I've got to restrict it so its range is between negative infinity and positive 2. So quick graph sketch. That's what the function looks like. And I've got to stop it there. I've got to stop it there at y equal to 2. All right. So to do that, I've got to work out what x value that is. So if I solve x squared minus 2 equal to 2, I'll get x squared is equal to 4, x equals plus or minus 2. So clearly it's the positive 2 number that we need. So that means the new domain will need to be from, well, positive 2 is the biggest number. So 0 is okay to positive 2, and that will give me a domain. Sorry, that gives me a range then. If I sketch this graph between those two values, I start there at negative 2, and I stop there at positive 2. So that gives me a range of negative 2 to 2, which is inside the domain of G, so we'd be all good there. So there's the restriction. To finish it off now in part 3, the rule of G of f of x, so where's G? Is G of f of x will equal square root of 2 minus whatever f of x happens to be, which in this case is x squared minus 2, which is equal to square root of 2 minus x squared plus 2, because that negative sign multiplies through, 4 minus x squared. So there's the composite function, and the new domain is the one we just discovered, which is 0 to 2. What have we got here? All right. We now have to sketch those graphs, and we just did a brief sketch, didn't we? All right, let's have a look. F of x equals x squared. G of x is 1 minus 4x. Find the composite function f of g of x. So we're just going to substitute g of x into f of x. So we'll go red into black. So if I just put 1 minus 4x into x squared, there's my f of g of x. We don't need to expand it, okay, unless it said leave it in a particular form. I guess if you wanted to, 1 Geez, what pencil's that one? 1 minus 8x plus 16x squared. But yeah, not necessary. Second one. Substitute f of x into g of x this time. So I've got my 1 minus 4x, and instead of putting in x, I'm going to have x squared there. So I just get, I guess I could tidy that up with 1 minus 4x squared. F of g of minus 1 is just substituting negative 1 into the functions that we've just determined, isn't it? So if I put negative 1 into 1 minus 4x all squared, I'll get negative 4 times negative 1, which is positive 4. 1 plus 4 is 5. Square it, I'll get 25. If I put negative 1 into 1 minus 4x squared, negative 1 squared is positive 1. Negative 4 times 1 is negative 4. And 1 minus 4 is negative 3. That's it for there. Okay, so we've got our simultaneous linear equations. So we have to find our exact solution, no solution, unique solution. So the process here, of course, is we want to compare gradients. All right, so the first thing that I've done, get my highlighter, we'll just go with yellow. I've rearranged 3x plus ky equal to 2 into y equals mx plus c form. Yeah, so I've taken the 3x across, divide everything by k, so I get 2 on k minus 3 on kx. That means the gradient of this particular line is negative 3 on k. If I do the same thing with k minus 2x plus y equal to k minus 1, get y equals k minus 1. I'll put it in a bracket so I don't sort of lose terms. And I'm going to subtract the k minus 2 term onto the right-hand side, which means the gradient of this line is negative, in brackets, k minus 2. So when we want to find our unique and no solutions, we want to compare the gradients. So we want to compare M1 equal to M2. Okay, and so where the gradients are equal, we know the lines are parallel and or possibly it's the same line. So if I solve -3 on K equal to -K on 2, and I'll do that in green. First thing I'm going to do is cross off the negative signs. And then I'm going to multiply the K across to give me 3 is equal to K times K minus 2. Let's expand this bracket to get K squared minus 2K. Then take the 3 over with the subtraction. And I get K squared minus 2K minus 3 equal to 0. Once I do that, I want to solve that expression equal to 0. So that gives me K equal K minus 3, K plus 1 if I factorise. Sometimes we'll need to use a quadratic formula. And that means I'll get K is equal to 3 or -1. So if K is equal to 3 or -1, it means that the gradients are the same. So if the gradients are the same and the y-intercepts are different, well, that means I just have parallel lines and no solutions. So if K is equal to 3, C1, the constant, the y-intercept of equation 1 is given by 2 on K, and that would be 2 on 3. If K is equal to 3 for C2, I'll get K minus 1, which is 3 minus 1, which is 2. So I get 2 different y-intercepts, which means I'm going to have same gradient, different y-intercepts, parallel lines. No solution. So K equal to 3 is a good thing. What about K equal to -1? Again, C1 will be just 2 over -1, which is -2. C2 will be -1 minus 1, which is also -2. So if K is equal to -1, we'll get the same gradient, but also the same y-intercept, which means it's the same line. So I get infinite solutions there. So as it says there in green, since the gradients are the same and the intercepts are the same, infinite solutions are at K equal to -1. So the only K value that gives me no solution is K equal to 3. So that's the answer I'm looking for. All right. Part B is, for what values of K does a unique solution exist? So a unique solution is going to be whenever the gradients are not the same. So we've just discovered that the gradients are the same when K is equal to -1 or 3, which means if K is anything except that, so if K is an element of R except for -1 and 3, we're going to get a unique solution. All right. Tech Active, you can obviously do a lot of these on your CAS, and the last one in particular, I've done a few CAS screen dumps. Maximal domain. So we can actually use a domain feature on the CAS. So if you go to your CAS and you just type in domain, f of x, I won't type it out, comma x, don't need the second comma, it will give you the domain of the function. So manually, we know that the denominator can't be 0 and that under the square root sign cannot be negative. So we need 4x minus 3 to be greater than 0, not equal to 0. So if we do that, 4x has got to be greater than 3, which means divide by 4x has got to be greater than 3/4. So round bracket 3/4 up to positive infinity, because I can't have 3/4 because that will give me 0. Question 2. I've got a function there, 4 minus 2x, and I've been given the range, and I need to find the domain. So in blue here, I've drawn the function, 4 minus 2x, y-intercept of 4, negative gradient. Okay, and I want to go to -2 to positive 10 on the y values. So positive 10 is going to be up here somewhere, and -2 is down there somewhere. So I need to find the corresponding x values to give me those y values. All right, so you can see there, if I solve 4 minus 2x equal to 10, I'll get x equal to -3. So that'll be the left-hand side. And if I solve 4 minus 2x equal to -2, I'll get 6 is equal to 2x, x is equal to 3. And that's the right-hand side. Yeah? And so if A is -3, B is equal to 3, that gives me a value of C in terms of the option. All right. Find the inverse. Again, we could, and you'll see I've done it on the next slide, if we solve, I might get rid of that one. If on the calculator we solve, even if I go swap the x and y, x equals 5 plus 1 over y minus 2 for y, that will give me the y equals 2 plus 1 over x minus 5. So that's one way of getting the inverse function using your CAS. If we do it technology free, swap x and y, what do I do there? So brought the 5 over to the left-hand side to get x minus 5 equals 1 over y minus 2. Because I have one term on each side, I can just flip them upside down. So I can make the left-hand side 1 over x minus 5 and the right-hand side just y minus 2. Then take the 2 across. So I get y equals 2 plus, probably should make that a bit clearer. Let's go. So 2 plus 1 over x minus 5. So the only two equations that are possibilities are option C and option D. Okay. So, and the difference between the two is the domains that they've got. Yeah. So obviously, if x minus 5 is in my denominator, x equal to 5 is the value that we cannot have, and so that makes it option C. Finally, okay, we've got simultaneous linear equations, and again, we want to find our unique solution, no solution. We could go through the whole process again, tech-free, okay, and get our equation 1 could be y equals 1 minus a minus 2x. Equation 2 could be 2.5a minus ax over a, and simplify things from there. Or if I go through the other two answers I'm interested in, so no solutions. If a is equal to -2 or 4, I get parallel lines and I get no solution, so it's option C. You can see some screen dumps that I've done, and I think this is probably the easiest way when you've got your CAS. If I rearrange each equation, I spoke about that previously, type in the equation and just get y equals, okay? I like that because I'm going to use those equations in a graphing process, all right? If I just solve those two equations, go to calculator and solve for x and y, you can see what x is equal and what y is equal to. And as complicated as it looks, the feature that here is most important is this line in here, a squared minus 2a minus 8, because they're in the denominator and it's those a values there equal to 0, sorry, the a values that give me that expression equal to 0, which will give me the unique solution, no solution, etc. So then I solve a squared minus 2a minus 8 equal to 0. I get -2 or a equal to 4. If I go into my calculator and put f of x equals 1 minus a minus 2x, because that's my y equals, f2 of x equals the other function, where it's y equals, and I create a slider in A. And if I slide my slider up and down, my lines will change. Yeah. Now I've given you snapshots of a equal to -2 and a equal to 4. And we can see in this instance, both of them at those values are parallel lines. So we knew from above that at a equal to -2 or a equal to 4, we get the same gradient What we weren't sure about is whether or not it was the same gradient and the same y-intercept. So clearly on the graph, we can see that they're different y-intercepts. So